Weiss from OSU to talk about Cassels Tate pairing.
Cool. Thank you very, very much to the organizers for giving me the opportunity to give this talk. I think I'm very happy to be giving this talk because it's forced me to learn something that I should have known for a long time. And that's what the Cassels Tate pairing is. And my goal today is going to be to define the Cassels Tate pairing. That's probably going to be the last thing I do in this talk. But the definition looks a little bit wild. So I want to spend the vast majority of this talk motivating why the Cassels Tate pairing and what's the key property of it that we really care about, and how does the definition of the Cassels Tate pairing come to solve that problem. So I want to start with the following setup. So E over Q is going to be an elliptic curve. And already in the sentence, I've made two vast simplifications. The first simplification is that I put Q here. If you want to do everything for a number field, you can, and virtually everywhere in my talk, if you replace a Q with a K, absolutely nothing is going to change. The second simplification is that E is an elliptic curve. You can do everything I'm going to say today for abelian varieties. There, you have to be a lot more careful. There will be some substantial changes, and in particular, one particular of the results that I'm going to mention is not true for abelian varieties, and I won't tell you which. Okay, so for our elliptic curve, famous theorem of Mordell-Weil, or in this setting actually just Mordell, is that the Q rational points of E are a finitely generated abelian group, and in particular, there's some infinite component and some finite component. And usually when someone writes this on the board, they're usually only interested in one of them, and usually the story is that the torsion part is relatively well understood and the rank part is the mysterious part. And we want some way of understanding the rank. And one of the main tools that we have at our disposal to do this is sum of groups. So if I let n be an integer that's greater than or equal to 2, I have this thing called the n summa group that we've defined. And sitting inside this n summa group are the Q rational points where I mod out by the Q rational points that are divisible by n. And the kernel of this map is the n torsion points in the so-called Tate-Shafarevich group. And the point of this exact sequence is I can use it to bound this thing if I know the size of this. And this thing will tell me the size of the rank. So what do I have? Well, the size of this. Well, that's just the same thing as the size of the n torsion times the n to the power of, I'm always going to get this backwards, and one of the sources has this backwards, n to the rank of e. This is going to be less than or equal to the size of the n summa group. So in particular, if I know the size of the n summa group and I know the torsion, which I almost certainly will, then this gives me a bound on the rank of the elliptic curve. But in general, this bound is not going to be a sharp bound. This bound will be sharp. So we'll get an equality if and only if the n torsion in the Tate-Shafarevich group is equal to 0. So if and only if the Tate-Shafarevich group is trivial. But fortunately or unfortunately for us, we have a conjecture. This says that this Tate-Shafarevich group is a finite group. And as an immediate corollary of that, well, this tells us that we can choose lots of n's with the Tate-Shafarevich group having no n torsion, because I have a finite group. So in particular, if I chose n to be a large enough prime, well, then this property will hold, and in that case, the P Selma group for that large P will exactly enable me to compute the rank of my elliptic curve. That doesn't tend to work all that well in practice, because at least if we're thinking in terms of arithmetic statistics, as soon as P gets basically bigger than 5, we don't really have any good ways of parameterizing the summa group, and therefore we don't really have any good ways of doing statistics with it. And on the other hand, for small p, well, we can't guarantee that the p torsion in the Tate-Shafarevich group is non-zero. But we have another strategy that we can use. So instead of trying to work horizontally with larger and larger p's, we can try and work vertically and work with, say, larger and larger powers of a single prime, say 2, for example. And then we can use another straightforward corollary to the fact this is a finite group, which is there exists an integer m, such that if I take my Tate-Shafarevich group and I multiply it by m, then I get the trivial. And how are we going to use this? Well, what's the idea? So I'm going to let m and n be integers that are greater than or equal to 2. Then I have a map that goes from the mn torsion of my elliptic curve to the n torsion of my elliptic curve. This is the multiplication by m map. And this map induces a corresponding map of Selma groups. So this induces a map from the mn Selma group of E to the n Selma group of E, again by multiplication by m. Okay, so sitting inside the n Selma group of E, I have EQ modulo NEQ. Sitting inside here, I have EQ modulo n MEQ. This map turns out just to be the quotient map, so the identity mapping. And mapping into both of these guys, I have just the rational points. And everything inside commutes. Why does that help me? Well, it tells me that if I have a point in here, there's 2 places it can come from. Either it can come from here, or it can come from something in shell. If it comes from here, then it comes from here, then it also comes from here. So what that tells me is if I have a point in the n Selma group that comes from a rational point, then it also is the multiplication by m of some point in the mn Selma group. So let me make that precise. Actually, I'll put it here. So the image of the rational points living inside the n Selma group actually lives inside m times the mn Selma group, living inside the n Selma group. And in general, the m times the cell mn Selma group, it could well be smaller than the Selma group. And in particular, if I have a strict inequality here, then I'm going to get a better bound on the size of the rational points than I would just by looking at the n Selma group on its own. So that leads to the following question. So what do I want to know? I want to know what is the image in general of the map that goes from the mn Selma group of E to the n Selma group of E. So in practice, how am I going to use this? Let's say for some reason I prove some really cool distribution as results about n Selma or 2 Selma. And now I want to bootstrap that up to say something about 4 Selma. So I already understand this group to some extent. And what I want to know is, well, if I have a point in this group, when is that point divisible by m? So let x be a point of the n Selma group of E. When does there exist x0 in the Selma group of nm with m times x0 equal to x? And if I can answer this question, well, I can use that to potentially give myself better and even sharp values on the size of my rational points. So I want to reframe this question a few more times before I try to answer it. and push that actually slightly towards. I can do that. So what I'd like to start by doing is just completing this exact sequence. So let's recall the question. I have a point x over here, and I want to know when is it the image of something here. And if I just take this sequence and turn it sideways, not quite this sequence. So this sequence and turn it sideways, I get two copies of this thing here, where this is the projection map. So this is surjective. And everything is over here. And I can start completing this exact sequence. So, okay. Let me try and ask you guys. Warm-up question. What is the kernel of this multiplication by m map? What goes there? Anyone?
The M torsion.
The M torsion, right? So this is going to be the inclusion of the M torsion in the N-M torsion. And if I multiply by M, then I get 0. So I can put a nice little 0 over here. Okay. Slightly harder question. What do I want to put here? So this one's a little bit tricky, and I think it fits into Alex's mantra of torsion sucking. Well, what I really want to put here is EQ modulo MEQ. Because that would be great, because then if I had that, then I could put this here. And this here, and then I'd be super happy. And I can put that there, but it's not going to be injective. And the problem is that there's going to be a little bit of torsion here. I'll have E, Q, N, modulo, MEQ. And then this is a multiplication by M. And I can complete that over here. This is going to be the same thing. Okay, that's the left-hand side of this exact sequence. And then the right-hand side of this exact sequence, well, there isn't so much I can say over here. Like the thing that I need to put here is just the co-kernel of this. It's just this modulo this, so it's going to be sha E n modulo m sha E m n. And then by chasing this through, well, the only thing that can go here is exactly the same thing. Okay. So this is my completed exact sequence. So again, what am I doing? So I'm starting with a point x over here, and I want to know when is there a point x0 that comes from the summa group of mn that maps to x. Well, that will be the same. X is in the image of this if and only if x is in the kernel of this. X being in the kernel of this. Well, okay. That means that, well, actually these things are sort of the same thing. That means that the image of x inside the n torsion of the Tate-Shafarevich group is divisible by n. In other words, x, its image of the Tate-Shafarevich group is divisible by n, yeah.
On the top left, why is MEQ even in the N torsion?
Why is, so, okay, what this really is, this actual kernel should be NEQ modulo NMEQ. That's what the kernel actually is. Yeah. And I can't cancel the n's just like that, but what I can do is I can say, well, there's a map that goes from this that maps to this, which is multiplication by n. And the kernel of this map is this.
Yeah, but the thing you're quotienting by isn't necessarily in the top.
Oh, okay. Whatever it is that makes it work.
Just put n. Yeah, this intersection. The bottom.
Yeah.
Okay.
EQ, like that. Fine. Okay. Happy?
Yeah, it's just.
Okay. Yeah. No, you're right. You're right. Okay. You know what? This is what I actually want to write. Let's do it like this. There we go. That's better. Okay. Any other questions? Okay, please do interrupt if you have questions. So, okay. So, what's the point? My answer will be positive. X will come from an mth image here if and only if x maps to 0 here, which is the same thing as x mapping in here to something that is an mth power. So, I can modify my question at the expense of erasing something. So my question now becomes, given X in the Tate-Shafarevich group, when does there exist an X0 in the Tate-Shafarevich group with M times X0 equals to X? And the slightly nicer thing about this formulation is that now I'm working inside a single group. I'm working inside the Tate-Shafarevich group, and I'm asking, when is X divisible by M in the Tate-Shafarevich group? I'm no longer constantly changing the group that I'm working with. I'm not asking when is X the image of something in some other group. I'm asking when is X divisible by M in a single group? And that's going to lead to a slightly easier formulation. And our answer is going to be the following thing. So there exists an alternating bilinear pair called the Cassels-Tate pair that pairs the Tate-Shafarevich group of E with itself into Q mod Z with the following property. Okay, so what is the property that I'm going to care about? Such that for all X in SHA E, X is divisible by M. So X is in M times the Tate-Shafarevich group of E. This. If and only if I pair X with Y, this is equal to 0 for all Y in the M torsion of the Tate-Shafarevich. So if we take for granted for a second that this pairing exists, we get an immediate corollary. Well, we don't get an immediate corollary. What it tells us is it tells us how to compute that X is divisible by M. X is divisible by M if and only if when I pair it with all Y in this conjecturally finite group, I get 0. And we can pull all of this back to answer our original question for the Selma groups. So I'm running out of board space. Now I think I really will cover this up. So here's a corollary. I'm going to let X be in the N Selma group. There exists then M is in the image. X is in the image of the Mn Selma group. If and only if I pair the embedding of X in the Tate-Shafarevich group with the embedding of Y in the Tate-Shafarevich group, this is equal to 0 for all Y in, well, whatever is the pre-image of the N torsion of the Tate-Shafarevich group. That's just the N Selma. So just unpacking this on the left is clear. On the right, if I have a point in the M Selma group, then I get a point in SHA M. If I have a point in the N Selma group, I have a point in SHA N. And if I pair those points with each other, I'm saying that X is in the image of the Mn Selma group, if and only if this pairing is 0 for all Y in the N Selma. So at least in principle, if I can construct this pairing, this answers my original question. I want to give a few more properties of this pairing, but before I do that, are there any questions? Okay. So I always feel when pairings are first introduced, it's always kind of tacitly assumed that you've seen them before. And in particular, when someone says what the kernel of a pairing is, you already know what that means. I think when I first heard these things, that definitely wasn't the case for me. So I'm going to write down this very crucial definition that for many of you will probably be completely trivial, but I'm going to write it down anyway. So I want alpha from V cross W to be a bilinear pairing, which is just a bilinear map. Then there are two kernels that I can consider of this pairing. So there's the left kernel, I'll call it ker left alpha. This is, well, if I fix a V, then I can view alpha as a linear map that takes elements from W to Q mod Z. And it's going to be the set of V in V, such that V comma W is equal to 0 for all W. In other words, it's going to be the set of V such that that induced linear map is the 0. And similarly, there's the right kernel. This is going to be the set of W in W, such that VW is equal to 0 for all V in V. And we'll say that a pairing is a perfect pairing if both of these are equal to 0. So there's no left kernel and no right kernel. And in particular, if I start with any pairing, well, I can always get a quotient pairing by quotienting on the left by the left kernel and the right by the right kernel, and that will give me a perfect pairing for my pairing. So let me give you a corollary of this theorem. So assume that the Tate-Shafarevich group is finite. Then the Cassels-Tate pairing is a perfect pairing. So it has no left kernel and no right kernel. I'll prove that it has no left kernel, and I'll leave the right kernel as an exercise. So, okay, because my Tate-Shafarevich group is finite, it has order m. The sum, I shouldn't use m, let S for sharp be the size of the Tate-Shafarevich group. Actually, no, I want to use m. Okay. And suppose that X is in the kernel. Of my pairing. Then by definition, if I pair X with Y, this is equal to 0 for all Y in SHA E. And in particular, it's equal to 0 for all Y in the M torsion of SHA. And now we look at our property. Well, if X pairs with Y to 0 for all Y in the M torsion of SHA, that's true if and only if X is divisible by M. Hence, X is in M times the Tate-Shafarevich group of E. But I chose M to be the order of the Tate-Shafarevich group. So by Lagrange's theorem, this is just equal to 0. And therefore, any element of the kernel is a 0 element. And that proves that the left kernel is trivial, and you can imagine proving the right kernel is trivial is not so much harder. Okay, so this is a perfect pairing. But somehow, for our original applications, we really do want to apply this to n-summa groups and m-summa groups. it's going to be helpful to cut down this pairing, and instead of view it as acting on the whole of SHA-E, maybe we want to view it as just only acting on the end torsion indication for image. So, here's some properties. So we can consider the restriction, whose name I'm not going to change. And this time it's going to go from SHA-E M plus SHA-E M to Q mod. So this is just the same pairing, but I've just restricted the domain. And I want to swap M and M for matching my nodes. When I do this, I'm no longer going to have a perfect pairing. When I do this, I'm going to have a kernel. Because well, I know that anything, for example, what pairs to 0 here? The things that pair to 0 here are the things that are divisible by M here. So the kernel, or the kernel of left kernel, is going to be M SHA-E MN. And similarly, the right kernel is going to be N SHA-E N. So this will no longer be a perfect pairing, but it's going to be a perfect pairing whose kernel does exactly what we defined this thing to do in the first place. Which is now I can, well, suppose I started with an M torsion point. How do I know that it's divisible by N? Well, if it pairs to 0 with everything that it's supposed to pair to 0. Yeah. Oh. Yeah. That's a really good question. So I think it's because of this if and only if. It's an if and only if. But you're right, otherwise it would be an only and if. Yeah. Any other questions? Yeah.
That you want that to be true for all y in the n subgroup?
Which bit? Over here?
Yeah.
So it follows from the one that I erased, the version of this for SHA.
You want it to hold for all y in the M torsion, is that correct?
So the N Salma group projects onto SHA EN.
Yes, you want it to hold for all M torsion or N?
Okay, am I mixing up M's and N's here? Is that the problem?
I don't know.
So this is correct. This should be, oh no, this should be an M. Because there's no N's inside. No, wait, no, hold on.
Probably that should be.
Yeah, that should be an M. That should be an M. Absolutely. Thank you for that spot. That should be an M. Yeah. No, okay. Yeah, so I got it right when I wrote it for SHA, but I got it wrong. I mixed up my N's and N's. So again, like, this is going to relate to what I'm about to write down. That if I take this pairing, well, I know that the N Salma group maps onto this thing, and the M Salma group maps onto this thing. And therefore I can get a corresponding pair. So lifting, we get a corresponding pairing that goes from the N Salma group across the M Salma group to Q mod Z. And now with that corrected version of the property, you can see that the left kernel is equal to the image of M, and the right kernel is equal to N times Fn. So this pairing is what allows us to answer the question that we started with. So what was our question? Just to remind you. So our question was if X is in the N Salma group, when is X in the image of the MN Salma group? And the answer is if, when I take X and I pair it with Y, I get 0 for all Y living where? For all Y. in the M sample. So that's the properties of the Cassels-Tate pairing. That's why we want to define the Cassels-Tate pairing. What remains is to define the Cassels-Tate pairing. Any questions? Okay. So, to define that pairing, I'm going to start by recalling some facts from Newman's talk, and I'm really happy that at the end of this talk he wrote down this kind of very convoluted exact sequence. I'm going to steal one property from that exact sequence, which we're going to really want. So we're going to build up the Cassels-Tate pairing out of local pairings. So let me remind you from Newman's talk about the Tate pairing. So there is a pairing. I'm going to denote by open brackets with a P that goes from H1QP, the amp, cross H1QP, the amp, to Q1Z. And just to make concrete, how is this defined? It's going to be defined in two steps. So the first thing I'm going to do is I'm going to map the product of these two things into H2. So first of all, I'm going to map into H2 QP bar square cross. And I'm going to do that using the cut product, but I can be really, really explicit about this. So I need to write down a cocycle that depends on these two. So I need to tell you where delta prime goes. And it's going to go to the cocycle. I'll call it lambda sigma tau, where lambda sigma tau, or lambda, where lambda applied to sigma and tau, is going to be, I'm going to take the mth Weil pairing of delta of sigma, composed with sigma of delta and tau. And you can check by hand that this is a 2 cocycle. You can check by hand that all of this is well defined. This is actually an exercise 10.24 in Silverman. If you do that exercise and you have my addition, there is a horrible typo in that definition where he doesn't have this sigma, and therefore nothing works. But otherwise, it's a really good exercise. And then step 2.
There's a typo in your
Oh, yeah. Okay. Very good. Thank you. And then secondly, I can use the very hard fact that follows from class 4 theory that this guy is actually isomorphic to Q1Z. And therefore, if I compose these two things, I get a map from this pair to Q1Z that you can check is a bilinear pairing. So what are some facts about this pairing? I'm going to use 2 of them. The first fact that I'm going to use is, well, living inside here is the image of the rational parts. That's EQP modulo M EQP. And I can ask, well, what is the orthogonal complement of this thing? What are the things in the right-hand side that pair with this to 0 on the left? And the answer to that is itself. So the image of the Kuma map is going to be orthogonal to itself under this Tate pairing. The second fact I'm going to use is something that Neven just about touched upon in the last part of this. So he started writing down a long exact sequence considering of 9 terms, the central 3 of which were H1 QEM maps to, I'll explain what this is in a minute, this restricted product of H1 QP EM. And this maps back to the dual of H1 Q EM. So what does this restricted product mean? It means that for all but finitely many primes P, the element has to live in the unramified part of this cohomology. So this is some collection of local cohomology classes, all but finally many which are unramified. And then what's this map over here on the right? So if I have some collection of cohomology classes, where am I going to map them to? I'm going to map them to the sum. I need to map them to a function from H1 QEM to Q mod Z, that's the dual. It's going to be the sum of the pairings of Z to P with this restriction. So I'll take an element here, I'll restrict it locally to QP, I'll pair it with psi P, and I'll add up all those pairings. And this sum makes sense, because for all but finitely many things here, I'm unramified. All but finitely many restrictions will be unramified, and even showed in this talk that if I pair two unramified classes with each other, I get 0. So this is actually a finite sum. The way that I'm going to use this fact is it gives me a way to show if I start with some collection of local classes, all but finitely many of which are unramified, when does that collection of local classes actually come from a global class? So when is something like this in the image of here? The answer is this is an exact sequence, if it's in the kernel of this. So let me write that down. I'm going to leave some spaces. So there. Suppose I have some collection of local classes living in this restricted direct product, so all but finally many of them are unramified. There exists an element, psi, that is a global element, that lists my local elements. So such that if I take the restriction of psi at P, that's equal to psi P for all P. This gap is here for a reason. If and only if I take this image and I pair it with the restriction of 1, that's equal to 0 for all y. And all that is saying is that the kernel of this map is the same thing as the image of this map. But I can go a little bit sharper than this. I can say, well, what if I don't necessarily care if my restrictions are equal on those? What if I only want them to be equal modulo the image of the rational parts? So if I put in, not just in H1 QPEM, but in the image of this modulo the image of the rational parts, then what do I have to change at the bottom to make that work? I'll leave as an exercise in kind of duality with the parent, but you can kind of believe, well, what's that going to do? Restriction, instead of it being true for all y in H1 QEM, is going to be true for all y for those elements of H1 QEM that have some analogous local condition. That'll be for all y in the sum group, the M sum group. So what we're going to take from this Tate exact sequence is this criterion that tells me that if I have some collection of local classes, and I want to know, do they live to a global class up to fudging by the image of the rational points? It gives me a concrete criterion for when that's true in terms of some sum of the Tate pairing. Okay, I think that's the most technical part of the talk so far, so any questions? Okay. So with that in mind, I can finally define the Cassels Tate pairing. So there's multiple different definitions of them, but I'm going to use, I think, the one that is most straightforward to get your hands on. And let me remind you about our setup. So we've got an element x in the Tate-Shafarevich group, and we have an integer m. And we want to know, when is x divisible by m in the Tate-Shafarevich group? Okay, let's just remind ourselves by definition. So what is the Tate-Shafarevich group? This is, by definition, the kernel from H1 QE to the product over all P of H1 QE. So in particular, I've chosen an element x that maps to 0. So x is living in here, and x maps to 0 everywhere here. That's what it means to be in the Tate-Shafarevich group. And the question that we were trying to consider is, when is x divisible by m? So when is x in M times the Tate-Shafarevich group? And we wanted to construct some pairing that would answer this question for us. So let me start with a little bit of a diagram. So the Tate-Shafarevich group sits inside H1 QE. This maps to H1 product QE. And by definition, the Tate-Shafarevich group is the kernel of it. And there's also a multiplication by M map over here. A corresponding multiplication by M map over here. And a corresponding map over there. And my starting point is that I have an element x over here. And I would like to know, when does x come from an element over here? Oh. So x is in here, so x is in here. And I'm going to make one huge simplifying assumption. So I want to know, does this x lift to something here? What I'm going to assume is at the very minimum, x lifts to something here. So I'm going to assume there exists an x0 in H1 QEM with in H1 QE, sorry, with m x0 equals x. And this assumption is a real assumption, but it actually happens to be true if m is prime, for example. So in particular, it's going to be true when m is equal to 2. If I want to do things without this assumption, I have to work a lot harder. And I don't want to do that. So my assumption gives me some element x0 over here. And what I'd like to know is, when did this element x0 over here come from something over here? In other words, if I take its restrictions, when are all of its restrictions equal to 0? So when does x0 live in the kernel of this? But I know by assumption that the images all lie in 0 over there, because x was chosen to be in the Tate-Shafarevich group. So I can pull back this exact sequence one more layer. So this is all part of the summer exact sequence that comes from the usual short exact sequence, e to e multiplication by m. So over here, I'll put H1 QEM that maps to the product of H1 QEM. I guess, almost. I can do one more layer. So this is going to be the rational points. And this is going to be all the local rational points. And there's some kernels. Okay. So don't want to just take the restriction of x0 because this restriction wasn't unique. This restriction is only well defined up to some element living here. Because if I were to place x0 by x0 plus the image of anything here, well, it's going to have the same image here. And therefore, it will still lift x. So what is the question we want? The question is, can we choose x0 so that res p x0 equals 0 for all p? Or maybe if I want to choose one fixed x0, then I can phrase this differently. Alternatively, does there exist a global element psi in H1 QE M such that if I take x0 plus, I'll call this map I of psi, this is an element of the Tate range. So I chose a lift x0, maybe my initial choice of lift was bad. Can I modify my lift by something in the kernel of this map so that it's good and actually lift? Okay. But by definition, whatever choice of x0 I made, it's lifting x. So whatever choice I make, whatever its restrictions are, they have to map to 0 here. And therefore, they have to come from some local element living over here. So by definition, whatever I chose my x0 to be, if I take m times the restriction of x0, that's equal to 0. So there exists a local element. And actually, I want to put a sign here, just to make things work later on, so I don't have to carry it around. There exists a local element zeta p such that if I take the restriction of x0 and I add it to the image of zeta p, then I get 0. And this is going to be true for everything. Now, this choice of zeta p also wasn't unique. This choice of zeta p was only well defined up to the image of here. So actually, I want to ask the following question. So, okay, going back. I'm trying to find some element zeta over here. That's my goal. If I can find an element zeta over here, then I can fudge. Okay, one more time. I've started with an x over here. I've lifted it to an x over here. I'm trying to know if there's a zeta that I can fudge my x0 by that's going to map to 0 here. I've chosen these zeta p's lifting x0 with the property now that, well, x0 plus I zeta p looks like it would do what I want. So if I can lift this collection of zeta p's, psi p's, to a global psi here, then x0 plus psi will have restriction 0 over here, and will map to x here, and then I win. So x will be divisible by m if and only if I can lift this collection zeta p to zeta, but not quite on the nose. I don't have to live it on the nose because there's still this kernel. So actually what I need, if and only if there exists an element zeta in H1 QEM such that the restriction modulo p of zeta is equal to zeta p, not necessarily on the nose, but modulo this kernel. in H1QP EM modulo the image of the reference. If such a thing exists, then I can lift my x. If such a thing doesn't exist, then I can't lift my x. And fortunately, we have a criterion for that. It's still on the board. Such an element exists if and only if this sum condition holds. So this is true if and only if I pair z to p with a restriction of y and take the sum, I get 0 for every y in my M sum group. And that is going to motivate my definition of the Cassels-Tate pairing, which I can finally define. Watch fire is. So I'm going to let x be an element of SHA En. So I'm going to define it on n torsion and m torsion, and you can believe that everything is compatible and it lists to something on the whole Tate-Shafarevich group. If you really want, you can take n large enough so that it is the whole Tate-Shafarevich group. And y in SHA En. Then I'm going to define my Cassels-Tate pairing from SHA En. I'm going to swap my n's and m's across SHA En to Q mod z as follows. By the pairing of x and y is going to be the sum over all p of this psi p that I construct by this whole recipe with the restriction of p of y tilde, where y tilde is any element of the M summa group that lifts y. I'll leave as an exercise to the interested reader to prove that this is actually well-defined. Proving that it's well-defined, parts of it are not so bad. Like, for example, the independence of this choice of lift and stuff like that. Other parts are a little bit of a pain. You actually have to dig into some of the properties of local duality. Because there were a lot of choices made here. I chose Z to P, I chose this lift, but all of those choices turn out not to matter. I get something well-defined here, but from the construction, it should now be clear that it has the property that I care about. I constructed this in such a way to guarantee that the only way that x can be in the image of M is if this pairing is 0 for all y in the M sum. And with that definition, I think I will finish. What do you mean by sensitive to local conditions?
Can I change some?
You mean in terms of like doing different kinds of summa groups?
Yeah.
Good question. I don't fully know the answer, but I know that these constructions are more general. So I'd assume that there is a kind of a different Cassels-Tate pairing that you could do. It's no longer going to be pairing SHA against SHA. It's going to be pairing some other thing against some other thing. Because you'd have to pair the summa group, whichever summa group you care about, with the corresponding dual summa group.
Yeah.
So in
Because I don't have the late pairing.
right. So well, yeah, because you don't have the Weiss pairing, and yeah. But the point is that you can do this. I mean, in one of Alex's paper, he does this in way more generality than this, working with kind of, in some sense, like much more general modules. And then there is a more general version of the Cassels-Tate pairing there. I don't know anything about that.
pairing that's symmetric?
Yeah, I don't think it's obvious with this definition. Like, sort of you can kind of believe it because the Tate pairing is antisymmetric, because the Tate pairing is antisymmetric, but I don't think it's, to me at least, it's not obvious from this definition that it's antisymmetric. Maybe there's something that you can show. It's also good that you said antisymmetric, by the way. That was the fact that it's true for abelian varieties, but I said alternating, and that's not necessarily true for abelian varieties. Any other questions?